Process pauses. Let's consider another example of dangerous clock use in a distributed system. Say you have a database with a single leader per partition. Only the leader is allowed to accept writes. How does a node know that it is still leader, that it hasn't been declared dead by the others, and that it may safely accept writes? One option is for the leader to obtain a lease from the other nodes, which is similar to a lock with a timeout. Only one node can hold the lease at any one time. Thus, when a node obtains a lease, it knows that it is the leader for some amount of time, until the lease expires. In order to remain leader, the node must periodically renew the lease before it expires. If the node fails, it stops renewing the lease, so another node can take over when it expires. You can imagine the request handling loop looking something like this. What's wrong with this code? Firstly, it's relying on synchronized clocks. The expiry time on the lease is set by a different machine where the expiry may be calculated as the current time plus 30 seconds, for example, and it's being compared to the local system clock. If the clocks are out of sync by more than a few seconds, this code will start doing strange things. Secondly, even if we change the protocol to only use the local monotonic clock, there is another problem. The code assumes that very little time passes between the point that it checks the time system.current time millis and the time when the request is processed. Process request. Normally this code runs very quickly, so the 10-second buffer is more than enough to ensure that the lease doesn't expire in the middle of processing a request. However, what if there is an unexpected pause in the execution of the program? For example, imagine the thread stops for 15 seconds around the line lease. Is valid before finally continuing. In that case, it's likely that the lease will have expired by the time the request is processed, and another node has already taken over as leader. However, there is nothing to tell this thread that it was paused for so long, so this code won't notice that the lease has expired until the next iteration of the loop, by which time it may have already done something unsafe by processing the request. Is it crazy to assume that a thread might be paused for so long? Unfortunately not. There are various reasons why this could happen. Many programming language runtimes such as the Java Virtual Machine have a garbage collector GC that occasionally needs to stop all running threads. These stop-the-world GC pauses have sometimes been known to last for several minutes. Even so-called concurrent garbage collectors like the hotspot JVM CMS cannot fully run in parallel with the application code. Even they need to stop the world from time to time. Although the pauses can often be reduced by changing allocation patterns or tuning GC settings, we must assume the worst if we want to offer robust guarantees. In virtualized environments, a virtual machine can be suspended, pausing the execution of all processes and saving the contents of memory to disk, and resumed, restoring the contents of memory and continuing execution. This pause can occur at any time in a process's execution and can last for an arbitrary length of time. This feature is sometimes used for live migration of virtual machines from one host to another without a reboot, in which case the length of the pause depends on the rate at which processes are writing to memory. On end-user devices such as laptops, execution may also be suspended and resumed arbitrarily, for example, when the user closes the lid of their laptop, when the operating system context switches to another thread, or when the hypervisor switches to a different virtual machine. When running in a virtual machine, the currently running thread can be paused at any arbitrary point in the code. In the case of a virtual machine, the CPU time spent in other virtual machines is known as steal time. If the machine is under heavy load, i.e., if there is a long queue of threads waiting to run, it may take some time before the paused thread gets to run again. If the application performs synchronous disk access, a thread may be paused waiting for a slow disk I/O operation to complete. In many languages, disk access can happen surprisingly, even if the code doesn't explicitly mention file access. For example, the Java class loader lazily loads class files when they are first used, which could happen at any time in the program execution. I/O pauses and GC pauses may even conspire to combine their delays. If the disk is actually a network file system or network block device such as Amazon's EBS, the I/O latency is further subject to the variability of network delays. If the operating system is configured to allow swapping to disk paging, a simple memory access may result in a page fault that requires a page from disk to be loaded into memory. The thread is paused while the slow I/O operation takes place. If memory pressure is high, this may in turn require a different page to be swapped out to disk. In extreme circumstances, the operating system may spend most of its time swapping pages in and out of memory and getting little actual work done. This is known as thrashing. To avoid this problem, Paging is often disabled on server machines if you would rather kill a process to free up memory than risk thrashing. A Unix process can be paused by sending it the sigstop signal, for example by pressing Ctrl-Z in a shell. This signal immediately stops the process from getting any more CPU cycles until it is resumed with sigcount, at which point it continues running where it left off. Even if your environment does not normally use sigstop, it might be sent accidentally by an operations engineer. All of these occurrences can preempt the running thread at any point and resume it at some later time, without the thread even noticing. The problem is similar to making multi-threaded code on a single machine thread-safe. You can't assume anything about timing, because arbitrary context switches and parallelism may occur. When writing multi-threaded code on a single machine, we have fairly good tools for making it thread-safe: mutexes, semaphores, atomic counters, lock-free data structures, blocking queues, and so on. Unfortunately, these tools don't directly translate to distributed systems, because a distributed system has no shared memory, only messages sent over an unreliable network. A node in a distributed system must assume that its execution can be paused for a significant length of time at any point, even in the middle of a function. During the pause, the rest of the world keeps moving and may even declare the paused node dead, because it's not responding. Eventually, the paused node may continue running, without even noticing that it was asleep until it checks its clock sometime later. In many programming languages and operating systems, threads and processes may pause for an unbounded amount of time, as discussed. Those reasons for pausing can be eliminated if you try hard enough. Some software runs in environments where a failure to respond within a specified time can cause serious damage. Computers that control aircraft, rockets, robots, cars, and other physical objects must respond quickly and predictably to their sensor inputs. In these systems, there is a specified deadline by which the software must respond. If it doesn't meet the deadline, that may cause a failure of the entire system. These are so-called hard real-time systems. In embedded systems, real-time means that a system is carefully designed and tested to meet specified timing guarantees in all circumstances. This meaning is in contrast to the more vague use of the term real-time on the web, where it describes servers pushing data to clients and stream processing without hard response time constraints. See Chapter 11. For example, if your car's onboard sensors detect that you are currently experiencing a crash, you wouldn't want the release of the airbag to be delayed due to an inopportune GC pause in the airbag release system. Providing real-time guarantees in a system requires support from all levels of the software stack. A real-time operating system RTOS that allows processes to be scheduled with a guaranteed allocation of CPU time in specified intervals is needed. Library functions must document their worst-case execution times. Dynamic memory allocation may be restricted or disallowed entirely. Real-time garbage collectors exist, but the application must still ensure that it doesn't give the GC too much work to do, and an enormous amount of testing and measurement must be done to ensure that guarantees are being met. All of this requires a large amount of additional work and severely restricts the range of programming languages, libraries, and tools that can be used, since most languages and tools do not provide real-time guarantees. For these reasons, developing real-time systems is very expensive, and they are most commonly used in critical embedded devices. Moreover, real-time is not the same as high performance. In fact, real-time systems may have lower throughput, since they have to prioritize timely responses above all else. See also latency and resource utilization on page 286. For most server-side data processing systems, real-time guarantees are simply not economical or appropriate. Consequently, these systems must suffer the pauses and clock instability that come from operating in a non-real-time environment. Limiting the impact of garbage collection. The negative effects of process pauses can be mitigated without resorting to expensive real-time scheduling guarantees. Language runtimes have some flexibility around when they schedule garbage collections, because they can track the rate of object allocation and the remaining free memory over time. An emerging idea is to treat GC pauses like brief planned outages of a node, and to let other nodes handle requests from clients while one node is collecting its garbage. If the runtime can warn the application that a node soon requires a GC pause, the application can stop sending new requests to that node, wait for it to finish processing outstanding requests, and then perform the GC while no requests are in progress. This trick hides GC pauses from clients and reduces the high percentiles of response time. Some latency-sensitive financial trading systems use this approach. A variant of this idea is to use the garbage collector only for short-lived objects which are fast to collect and to restart processes periodically before they accumulate enough long-lived objects to require a full GC of long-lived objects. One node can be restarted at a time, and traffic can be shifted away from the node before the planned restart, like in a rolling upgrade. See Chapter 4. These measures cannot fully prevent garbage collection pauses, but they can usefully reduce their impact on the application.